Hey guys, welcome back to the Blimp video channel. My name is Craig Enders and I appreciate you tuning in. In this video, we're going to talk about fitting multi-level structural equation models in Blimp. In a different video, I demonstrated Blimp's multi-level modeling features, and the model setup for that video was consistent with the linear mixed model tradition. So in this video, I'm going to show you a different way to set up that model, and we'll compare and contrast the results. Before we get started, I want to acknowledge the Institute of Educational Sciences for their support and point you to the project's website. You can download Blimp at the same homepage. Click the subscribe button in YouTube to get notifications when I post new videos. So let's jump in. To make the illustration more concrete, I'll use a dataset from an educational study with repeated measurements at level 1 nested in students at level 2. Researchers collected up to 7 monthly assessments of math self-efficacy and math achievement test scores, and there's a person-level binary predictor that codes whether the student was in the experimental or control condition. As a refresher, the previous multi-level modeling video used a random coefficient analysis where the influence of the time-varying self-efficacy scores varied across persons. Efficacy was decomposed into unique within and between person effects by centering the level 1 scores at the level 2 person averages, then including those means as a level 2 predictor. In the path diagram, I use black dots to represent the random intercepts and random slopes. Before we look at the multi-level SEM setup, I want to quickly look at the Blimp script for the earlier analysis. And I want to draw your attention to a few important commands. First, the cluster ID command specifies the student level or level 2 identifier variable. If you recall from the data table, the intervention assignment code was complete. Listing this variable on the fixed line tells Blimp that the predictor does not require a model for missing data imputation. Next, the center command instructs Blimp to center self-efficacy scores at the latent variable representations of the level 2 group means. Finally, the model command gives the regression equation. Appending the .mean function to the efficacy variable inserts the latent group means as a level 2 predictor, and then listing efficacy to the right of the vertical pipe specifies a random slope for that variable. Now that we've refreshed ourselves on the mixed model setup in Blimp, let's take a look at the multi-level SEM. To illustrate the latent variable version of a multi-level model, I use level 1 and level 2 notations similar to that from Raudenbush and Breich. The focal model is a simple regression with group mean-centered efficacy scores as the predictor. The J subscript on beta 0 and beta 1 indicate that each person has a unique intercept and slope. We also need an equation for efficacy because this variable has missing data. That equation says that each level 1 efficacy score is a function of the person's own average plus a time-specific residual. The orange symbols in the equations highlight 3 latent variables in the model, which I represent as circles in the path diagram. Finally, I use the latent command to define the 3 student-level latent variables. Recall that student is the variable name for the level 2 index variable that differentiates individuals. Including this variable to the left of the equal sign tells Blimp that these variables are at level 2. Let's revisit the level 1 models and see how to set them up in Blimp. Let's start with the efficacy model. In Blimp, you refer to the mean or intercept using the number 1 to the right of a tilde. In the model statement, I'm saying to set the mean equal to the level 2 latent variable. Blimp automatically introduces the level 1 residuals, so there is nothing else to specify. Finally, the dashed arrow in the path diagram depicts this part of the model. Next, let's look at the focal regression equation. First, I set the intercept equal to the beta 0j latent variable, just like I did in the efficacy equation. Efficacy scores are centered at their group means at level 2, and the random slopes are represented by the person-specific latent variable beta 1j. In parentheses, I manually center the predictor by centering the level 1 efficacy scores from their corresponding group means. I then use the @ symbol to set the slope equal to the beta 1 latent variable. The dashed lines in the path diagram illustrate this part of the focal model. Moving to the level 2 model, let's take another look at the 3 latent variables. We also need to specify models for those variables. One of the key features of the multi-level SEM is that the latent variables have non-zero means. These latent variable means correspond to the fixed effects from the linear mixed model. By default, Blimp assumes that latent variables have means equal to 0. Listing a 1 after the tilde overrides this default and instructs Blimp to estimate the latent variable means. Finally, we usually assume that the random intercepts and random slopes correlate. The last line with the double tilde says to correlate the beta0j and beta1j latent variables. In the path diagram, the curved arrow represents this latent variable correlation. Next, let's fill out the level 2 regression equations. Remember that the condition indicator and the efficacy person means predicted the math outcome in the focal regression model at level 2. These variables enter as predictors of the random intercepts in the beta0j equation. The dashed arrows in the path diagram show these slopes. In Blimp, latent variables are just missing data that need to be imputed. As such, the level 2 efficacy person means need their own regression equation. Although we don't really care about the relation between the efficacy means and the intervention indicator, that association still needs to be in the model. Essentially, we need to link the incomplete latent variable to other predictors at level 2. The dashed line in the path diagram shows the regression slope. We now have everything that we need to fit the model, so let's take all those chunks of code and put them together. The syntax on this slide shows the full set of model commands. In another video, I explained that each outcome variable has its own table of estimates. In this case, this means every model to the left of a tilde has a table of results. By default, Blimp orders those tables alphabetically, which may not be the optimal way to go. I use labels ending in a colon to arrange the order of the output tables. Blimp will order the tables following these labeled model blocks. That is, the latent variable regressions for beta0j and beta1j will be the first tables of results, followed by the next two blocks. Now let's expand the model by specifying a random coefficient model with a cross-level interaction. We just need to add one line of code to the Blimp syntax to do this. The previous video on linear mixed models used a model where the level 2 intervention code moderates the level 1 influence of self-efficacy on math achievement. The regression equation and path diagram look like this. The diagram depicts the cross-level interaction with a directed arrow pointing from the condition rectangle to self-efficacy's random slope. Those random slopes are shown as black dots on the straight arrows. In the latent variable framework, there is no product term. Rather, the condition dummy code predicts the beta1j latent variable. Recall that beta1j is itself a bivariate association between efficacy and math achievement at level 1. Thus, the equation saying that the magnitude of that within-person association depends on or is moderated by the experimental condition. The dashed arrow in the path diagram corresponds to this cross-level interaction effect. A previous video in the series gave a tour of the Blimp output, including tables of regression model parameters. The composition of those tables is identical in a latent variable model. Whereas all of the predictors from a linear mixed model appeared in the same table, though, they're now spread out across multiple tables. So Blimp prints specific summary tables for each of the latent and manifest variables in the model part of the script. So let's take a look at that. This is a table of results for the beta0j random intercept latent variable. The intercept from the coefficients section corresponds to the fixed effect intercept in the linear mixed model, and the two slope coefficients capture the between cluster effects of the efficacy group means and the experimental condition. Finally, the variance is the unaccounted for random intercept variation at level 2. Next, this is a table of results for the beta1j latent variable. The intercept from the coefficients section corresponds to the within cluster fixed effect slope from the linear mixed model, and the condition coefficient is the cross-level interaction effect. The variance in this section is the unaccounted for random slope variation at level 2. The final table in the between cluster block is a table showing the covariance and correlation between the random intercepts and slopes. Finally, the output table here shows the within cluster part of the model for the math achievement variable. In this example, the within cluster residual variance is the only parameter of interest from the table. Now that we've seen how to fit a multi-level model in both the mixed modeling framework and the SEM framework, it's useful to see how they compare. So let's take a look at the two sets of results. This table displays the Bayesian point estimates and measures of uncertainty from the multi-level model and the multi-level SEM. As you can see, the differences are trivial and typically in the second decimal point. There's essentially no reason to prefer one approach over the other. That concludes our brief tour of the multi-level SEM model in Blimp. This video only scratches the surface of what you can do with multi-level SEMs. Models can include additional outcomes and predictors, as well as latent factors with multiple indicators. Blimp's estimation architecture also allows you to have three-level models, mixtures of discrete and continuous variables, path and latent variable models, and models with heterogeneous within-cluster variation, among other things. A detailed user guide with numerous other examples is available by choosing the Help option from the Help pull-down. Thanks again for tuning in, and I hope you check out future videos.